Okay, I'm going to start this video with some things you've already seen, but then in the second part of this video I'm going to talk about ordinal numbers. So I don't want to cover everything in chapter 3, but I want to kind of show you, some of the cool parts. So, but before I do that, let me just start with, countably infinite, uncountably infinite, and the real numbers. Why were the real numbers uncountable? Okay, so so remember, countable means either finite or countably infinite, and countably infinite means there is a bijection from, say, the positive integers to your set. Okay, so let's call our set A. So if A is countable, then it's either a finite set, let's say 1,000 elements or 1,000,000, and if it's countably infinite, that means there is a bijection from the positive integers to our set A. Okay, so now we've learned that R is uncountable. Okay, so for finite, finite cardinal numbers. So for finite cardinal numbers, we use these cardinal. For finite sets, we use these cardinal numbers: 0, 1, 2, 3, and so on. But these are finite cardinals, and this here is an infinite set. So none of these cardinal numbers describe how many elements this set has. So since none of these numbers describe the number of elements here, we needed a new number, and we'll just and the notation we use for that is R of 0. So R of 0 denotes the number of elements of this set. But if there's a bijection between this set and this set, like for example here I have a bijection between the fingers on my left hand and the fingers on my right hand. If you have a bijection, then you know that two sets have the same cardinality, even if you don't count how many there are. Okay, so any set that has a bijection with this set will have this cardinality. So now if we claim that R is uncountable, well, it's definitely an infinite set, so the cardinality is not one of these. And if I claim that R is uncountable, then it's not this cardinality either. So then we need a new symbol to denote this cardinality. And we've used the letter C for the cardinality of the reals. The letter C refers to continuum. Now, how do we know that the reals were uncountable? Well, if they were countable, well, then they're countably infinite, and that means there should be some bijection like this. So why couldn't that exist? I mean, after all, there are infinitely many numbers here, and there are infinitely many real numbers. So let's see. So why can't this happen? Okay, so let's say here's the set of real numbers, and here's the set of, say, positive integers. Integer number 1, integer number 2, integer number 3, integer number 4, etc. So let's first see how would I get a function from this set to this set. Well, then 1 has to go somewhere. So I just have to pick some element. I don't know. Let's say square root of 2. Okay, and I'll just this one has to go somewhere. Okay, and then this one has to go somewhere. Well, maybe this one goes to, say, pi, right? And let's just call these numbers. So this here is f1. This here is f2. This here goes to some number, and that would be f3, etc. Okay. So anytime if I take a function from here to here, then I'm getting an infinite sequence of real numbers. Real number f1 is a real number, f2 is a real number, f3 is a real number, and I get an infinite sequence an infinite sequence of real numbers. Now, why do I say that all these real numbers combined, even though there's infinitely many, why is it not possible that all of these combined is all real numbers? Okay, so the proof like that worked like this. Okay, so we're gonna construct a new real number. Let's say that starts with a 0 and then a dot and then some digit and a digit and a digit and a digit, etc. Okay, so and let's say that f of 1, let's say that 1 went to square root of 2. Okay, so square root of 2 is 1.4142, etc. Okay, now I'm gonna pick this digit and I'm gonna make it different from this digit. So let's say if I have a 4 here, let's just make this, I don't know, like a 9 or whatever. But in any case, this one and this one, I'm going to choose this one so that it doesn't match that number. Okay? So in other words, I'm going to choose this number in such a way that b is not equal to the first real number that I picked. Okay? And now this has so you can put here whatever you want, but just don't put a 4 here. Let's just put I don't know, let's say 9. Okay? And now the second real number that I picked is pi, is 3.1415, etc. And now I'm going to look at its second. I'm going to look at the second digit here, and the second digit here. And now I'm going to just make sure that this digit is not equal to that one. So this one here should be not equal to that one. Okay. So pick anything, but just make sure you don't pick that. Okay. So let's say 7 or whatever. Okay. And then let's say the third number that I picked, let's say that was f3 equals something dot something 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 something, etc. Now I'm gonna look at its third digit, and I'm gonna look at the third digit here, and I'm just gonna choose whatever this number is. I'm gonna put something different there. So make sure that this number is not the same as that one. So because the way I chose the first number, the way I first chose the first digit ensures that b is not f1. The way I chose the second digit ensures that b is not f2. And the way I chose the third digit ensures that b is not f3. And then likewise choose the fourth digit to make sure that b is not f4, and so on. So what you end up getting here is a real number. It's an infinite a 0 and a dot and an infinite string of digits. That's what the real number is. So you get a real number, and it's not any one of these. So if I look at if I apply f to all the positive integers, then I get this entire sequence. So I get an entire sequence of numbers in here, and I have a new number that's not one of those. So let's recap this a little bit and see what happened. Okay, so I had let's make this a little bit bigger. I had took the set of all real numbers, and I just picked some element. Let's say element number 1. Okay, and then I picked another element. Let's call this element number 2. Okay. So f2 is just some real number. You can choose whichever one you want. Okay, and then let's choose another real number and another real number, and so on. Okay, and then we made this number b, but we picked the first digits to make sure that b is not f1, and then we picked the second digit to make sure b is not f2. So no matter how you choose these real numbers, after choosing an entire infinite sequence of real numbers, there are more numbers left that aren't in your sequence. Okay, so so even after you pick an entire sequence of real numbers, there is still another number out there that isn't in there. Now you could have said, wait a minute. What if I just modify my sequence and insert this one right at the front? So let's make a new sequence, say B, and then F1, F2, F3. Now I have an infinite sequence and B is in there. But here's the kicker. You can apply the same trick to that new sequence. Okay? So for this new sequence, you can just apply the same trick and it will give you another number not in this sequence. So if I call this B, let's rename this now B1, then the same trick gives me another number B2 that isn't in here. Okay, so but then you say, wait a minute. Okay, so this sequence is B1 and then the old sequence. Well, you can say, well, wait a minute. I can make a sequence that has all of these numbers and these two and also these two. Let's say this one. Let's say take the sequence B2 and then B1 and then the old sequence. Well, that has all these numbers in it and these numbers. But now we can apply the same trick, okay, the same trick to construct a number that is not in this sequence either. So in other words, there is still another real number out here that isn't in this sequence. So let's just pick one of those and let's call it B3, okay? And now you can see where this is going. This just repeats itself, so there must still be another real number out there, B4, B5, B6, etc., and so on. So how many real numbers did I find yet? There's all of 0 of them here, and there's all of 0 of them here. So all together, I found all of 0 plus all of 0 real numbers. So that's how many we've selected so far. But you know, all of 0 plus all of 0 is all of 0. So all of these real numbers, they still fit in a sequence. Well, I have to do something a little bit different than this, but I can make this sequence, say B1 and then F1, and then B2 and then F2, and B3 and F3. Now, I mean F of 1. Okay, so let's continue. I had my phone on silent mode because I thought that would prevent phone calls, but actually it didn't. So I have to. I'll just have to slice these two videos, concatenate these two videos together. In any case, so where were we? Okay, we had selected an infinite sequence of real numbers. Turns out that couldn't possibly be all real numbers. So there must have been another one, and another one, and another one. So there must have been another all of 0 more real numbers. But all of 0 plus all of 0 is all of 0. So if we select two sequences of real numbers, then all of that combined still fits in one sequence. Namely, what sequence would that be? Well, like it's the same as how you fit two hotels infinity into one hotel infinity. Okay, the original guest gets, say, the even number of rooms, and the new guests get the odd number of rooms. So for example, if these are the original guests, then they get the even number of rooms, and if these are the new guests, then we can give them the odd number of rooms. So B1 and then B2, etc. So all of these real numbers combined still fit in one sequence. And because they fit in one sequence, I can once again apply the same trick like before, apply that to that sequence. So I'll just make sure that this number now is maybe not the same as it is now, but it's different. I'm going to make sure that I'm going to put something here that's different from the first digit of the first member of my sequence. And this one's going to ensure that B is different from the second member of the sequence. So once again, we'll get a real number B that must be different from all of these real numbers. So I'll get once again some number B here. And then once again, that number could be placed in front of this sequence. You could apply the same trick again, and therefore there must be yet another one and another one. But now I have now a little bit of a problem. I'm kind of starting to run out of labels. You see, I've already used index 1, index 2, index 3. So yeah, what label should I give here? I mean, if I because now I'm getting sequences of sequences of sequences. Okay, so how do I label these things? Okay, so so for that we use ordinal numbers. So let me get a fresh page and describe. Okay, so ordinal numbers. So what are ordinal numbers? Now remember, cardinal numbers are just about how many elements does a set have. But here now I'm looking at sequences. And so if I pick a sequence of real numbers, like for example this first sequence, then it has a first element, second, third, fourth. So ordinal numbers are about ordering. Which element did we pick first? Which element did we pick second? Okay, so cardinal numbers are like say 0, 1, 2. So 1, 2, etc. So cardinal numbers tell you, for example, how many runners were there in a race. Ordinal numbers are about who was first, who was second, etc. So if I'm going to pick a sequence of real numbers and I want to keep things organized, I need to have ordinal numbers. I want to keep track of which number I picked first, which number I picked second, which number I picked third, and so on. Okay, so let's again take real numbers and let's pick elements in them. And as you've seen, it seems like we're never going to run out of elements because, at least initially, because I can always apply this trick, right, and get another real number. So let's start choosing real numbers. So let's say here's a set of real numbers, and yeah, should I start with 0 or 1? Okay, well let's start with 0. Just pick any real number. Let's call it B0. Now let's pick another real number, different from this one, and let's call it B1. And we keep on going and so on. So we get an infinite sequence. The first number I picked, the second number I picked, the third number I picked, okay, and so on. So I get an infinite sequence of real numbers. But as we've seen, that sequence couldn't possibly contain all real numbers. So after I pick, it's kind of strange to say this, after picking infinitely many elements, okay, how could you possibly have something that comes after infinitely many steps? But nevertheless, if I, for example, if I just give you any injective function from the positive integers to R, then I really did select infinitely many elements. And as we've seen, there are more still. So after picking infinitely many elements, there are more elements that I can pick. But now I need a new label for that, because I've already used up the number 0, 1, 2, 3, 4. So I just need a new number. And this shouldn't be Aleph 0, because even if I pick 100 more elements, the total number of elements I've picked is still always going to be Aleph 0. You see? Like in this drawing, if I pick Aleph 0 elements, and then even if I pick another Aleph 0 elements, then I still only have picked Aleph 0 elements. But I don't want to give all these things the same label, so I can't use cardinal numbers for these labels. So I got to use something else, and that's called ordinal numbers. So instead of calling this element number Aleph 0, we're going to call this element number omega. Okay? So we've picked infinitely many elements. Okay? And namely Aleph 0 of them. Okay, that's how many. And then after, one for each non-negative integer. And then after that, there were still real numbers left. So the first one I pick after that, I'm going to call that element number omega. But again, there are still elements left. So the next one, I'll just label it omega plus 1. So so basically, element number omega plus 1 is what? Well, first I selected an infinite sequence of real numbers. Then I selected another one, and omega 1, and that one is element number omega, and the one that came after that is element number omega plus 1. And then, of course, I could pick element omega plus 2, because as we saw before, you're not going to run out of real numbers anytime soon. There really are a whole lot of them. So so I can keep going. I have element number omega plus 2, element number omega plus 3, etc. And I get another infinite sequence. But that infinite sequence also has only Aleph 0 elements. And this first infinite sequence had Aleph 0 elements. So combined, this has Aleph 0 plus Aleph 0 elements. Okay? So so if I reorganize these sequences, so if I merge the two sequences, just like the Hotels Infinities, like I took this sequence and I merged them into one sequence, then I find that all these elements fit into a single sequence. But the point is, if you do that, it changes the ordering. And ordinal numbers are all about how things are ordered. Okay, so if you have two sets of runners, two sequences of runners, and now you merge the two sequences into one sequence, you know, you have a sequence of runners here, runner 1, 2, 3, 4, etc., and I have another sequence of runner 1, 2, 3, 4, etc. And if I merge the two sets of sequences of runners into a single sequence, then it changes the ordering. So if I only care about how many elements there are here, well, then I have Aleph 0 plus Aleph 0 equals Aleph 0. Okay, you can just merge the sequences into one. But if I want to preserve the ordering, then I can't do that. Then I just have to leave it as it is. And of course, these, yeah. So what am I trying to do? So why am I saying that these ones can fit in a sequence, even though I don't want them to put them in a single sequence? Because the fact that they can fit in a single sequence, then I can use the same argument again from here to show that there must still be more real numbers. So apart from all of this, there must still be another number. Let's call it omega. Well, I guess I need a new label. Let's call that label omega times 2. So then the next one will be omega times 2 plus 1. And then omega times 2 plus 2. And so on. Okay. So after this infinite sequence, we get element number omega times 2, and after that you have element number omega times 2 plus 1, and so on. Yeah, and yeah, how long does that keep going? Well, yeah, you see. So let's now look only at the labels. So we have 0, 1, 2, etc. And that's already an infinite sequence. And then after that infinite sequence, we have omega, and then we have omega plus 1, omega plus 2, and that's another infinite sequence. And then we have omega times 2, omega times 2 plus 1, etc., another infinite sequence, and then we have omega times 3, and you can with an infinite sequence, and then omega times 4. And of course, at some point, we're going to get omega times omega. But that is nowhere near the end. That's actually still countably many ordinal numbers. So, you know, at some point you'll have omega square. Okay, this is omega square. And then omega cube, omega to the fourth, etc. And then at some point you have omega to the omega, and so on and so on. So, so now. So it doesn't stop here. This keeps on going way further. But in any case, what we've seen now here, these are examples of ordinal numbers. Okay. So we just use cardinals if we don't care how things are ordered and we just want to say how many there are. But we use ordinals if we do care how things are ordered. Okay, we have a first element, the second element, the third element, the fourth element, and after all of that, we have an omega element, an omega plus 1th element, an omega plus 2th element, etc. And after all of that, we have an element number omega times 2, an element number omega times 2 plus 1. Okay, and so that's what ordinal numbers are. They describe the order in which you've picked elements from a set. So now, chapter 3. So I don't want to cover all of chapter 3. I just want to, kind of get to the good stuff. So I'll just give a brief summary of ordinal numbers, like how would we define ordinal numbers and what are their properties. Okay, so now before I even define ordinal numbers, I just want to define their ordering. Okay, so each ordinal number will be encoded with a set. So an ordinal number will just encode with a set. In fact, in pure set theory, the only things that they allow there are sets. So in fact, in pure set theory, everything is encoded with a set. In other words, in pure set theory, everything is actually a set. If I want to pick some ordinal number, I'll just use Greek letters. So whenever you see me write a Greek letter, it means that's going to be an ordinal. That's going to denote an ordinal number. So let's say if I pick two ordinal numbers, and I want remember, ordinal numbers is all about, in what order came things. Who was the first runner? Who was the second runner? Okay, the ordering is the key thing that's important about ordinal numbers. So when would we say that an ordinal number alpha is less than an ordinal number b? Okay, so the definition is the following. We say that alpha is less than b when alpha is an element of b. Now that at first looks really strange, but remember, in set theory, the only thing we actually allow in set theory are sets. So everything in set theory is encoded with a set. So even numbers are encoded with some set. Okay, so we say, our definition is, we say that so if alpha and beta are ordinal numbers, and if I write this, then this here is a statement, and in other words, this statement is either true or the statement is false. And we'll define this statement to be true if alpha is an element of beta. Now, what is alpha less or equal beta? Well, we define that in the following way. This is true if alpha is less than beta, which in other words, alpha is an element of beta, or when alpha is equal to beta. Okay, so that's how the ordering is defined. Now, you may wonder, is the following possible? Could it be that alpha is less than beta, and so that's a question mark. Could it be that alpha is less than beta and beta is less than alpha? Well, I didn't spend a lot of time on the axioms of set theory, but I did write this handout, the ZFC axioms of set theory. And if you look in there, it's the so-called regularity axiom forbids this. So the answer is no. This cannot happen because of the so-called regularity axiom. Okay, so in other words, really bad properties. So this definition is not going to have some really bad properties like this. Okay. So potentially this is a reasonable ordering. And now I'm going to define ordinal numbers in a way that looks very much like I told you not to do. Okay. Namely as follows, and this is the von Neumann way to define ordinals. So an ordinal is the set of all smaller ordinals. The set of all smaller ordinals. Okay? Now remember, in math there is one thing that is absolutely forbidden, which is a circular definition. Okay? You cannot define something in terms of the thing you're trying to define. Okay? So if you're trying to define something, you must also not use the thing you're trying to define. And it very much looks like this is violating that rule. Because it looks like in this definition, I'm trying to define what an ordinal is, and it really looks like I'm actually already using what the definition is. So this definitely looks circular. Okay? And remember, why are circular definitions forbidden? Because it leads, if you allow circular definitions, you get a huge number of contradictions. So for example, Russell's paradox. But also, so if you forgot what that is, that you can find it on page 30. So Russell's paradox, you get that paradox because it starts by Russell's paradox starts with the set of all sets, but that's circular because if you want to define the set of all sets, you kind of already need to know what that set is because it's one of those sets. So if you allow the set of all sets, then Russell showed that leads to a contradiction, and it's in a way not terribly surprising because it's a circular definitions, and circular definitions there are many ways that that can lead to contradictions. So we should be extremely suspicious of this definition because it really looks circular. But nevertheless, it actually does work. So I think that's, I don't know, I just think that's really cool. So let's just go with this definition rather than the safer definition that you would find in most texts. Okay, so let's just go with the quote-unquote dangerous definition. Okay, according to this definition, what would be the smallest ordinal? In other words, the first ordinal. Okay, so the smallest ordinal, it is, according to von Neumann's definition, it is the set of all smaller ordinals. But wait a minute. But I'm trying to find the smallest ordinal. So this is the set of all smaller ordinals. Okay, according to von Neumann's definition. But if you already have the smallest ordinal, then there aren't any smaller ordinals. Okay. So there are no such thing as, if I'm trying to figure out what the smallest ordinal is, then there is no such thing as an even smaller ordinal. So this is blank. So the smallest ordinal is the empty set. Okay, that's what you get from von Neumann's definition. So now what is the next smallest? Okay, the second smallest. Well, let's look at von Neumann's definition. It's the set of all smaller ordinals. But if you want to figure out what is the second smallest ordinal, well, there's only one ordinal that's smaller still. And we need to take the set of all smaller ordinals. Okay? So I need to take a set of all smaller ordinals, but the only one that's smaller than this one is the very smallest one, which is that. Okay? Now, what's the next one after that? The next smallest. Well, it's a set of all smaller ones. So that includes the very smallest one, which is that one, and it includes the second smallest, which is that one. Okay. And now next one. Well, the next smallest is what? It's the set of all smaller ones. So which ones are smaller? Well, that one. And then this one. And then also this one. Now, at this point, it gets kind of long to write all of this, so I'm going to need to introduce some abbreviations. Because let's say if I want to write the next one, that's what? It's a set that contains this guy. Okay, that's not too much work to write. And then this guy, well, it's a little bit more because I have these curly brackets. And then I have to write this guy. I could still copy that, but then I also have to write this guy. So if I want to write this one down, I have to write this guy and this guy and this guy and this guy. And that's just not going to fit on this line. So I'm going to need some abbreviations, okay? Abbreviations. Okay, I'm going to abbreviate this guy as 0. So 0 is short notation for that. Okay, it's only a little bit shorter, but okay. And I'm going to abbreviate this guy as 1. And I'm going to abbreviate this guy as 2. So that already allows me to write this one in a much shorter way. So this one is now, okay, this is abbreviated as 0, this second element is abbreviated as 1, and this third element is abbreviated as 2. Okay? But and this whole thing, well, you can guess how I'm going to abbreviate that. I'm going to abbreviate that as 3. And then now, the next one is the set of all smaller ones. So it's this one, which I'll abbreviate like this. It's this one, which I'll abbreviate as this. It's this one, abbreviated as this. And this one abbreviated as that. And of course, I don't want to keep writing this over and over again, so I'm going to abbreviate this as 4. Okay? So, and so that's how it continues. So the next one will be 0, 1, 2, 3, and this new one, which I denoted as 4. This is going to be just too much work to keep writing that. So instead of writing this, I'm just going to write 5. Okay? So now let's look at this list of ordinals that I found so far. So 0, 1, 2, 3, 4, 5, they're actually sets, right? So 5 is just a short notation for this set. 0, 1, 2, 3, 4. 4 is short notation for this set. 3 is short notation for this set. But this here is short notation for this set. 2 is short notation for this set, and 1 is short notation for this set, and 0 is short notation for that set. Okay, but I'm gonna have to use this short notation, otherwise things are gonna get impossibly long. So what ordinals did we find so far? 0, 1, 2, 3, 4, and so on. Now, what about this ordering? Is that all ordering? Yeah, because, for example, 3 is indeed an element of 4. Okay, so if I abbreviate 4 as this here, what we get is 3 is indeed an element of 4, because my ordinal 4 is really just this set, and my ordinal 3 is in there, so 3 is an element of 4. So if we go with this definition, we get 3 is less than 4 according to this definition. So the definition works out exactly the way we want to. Okay, now here we have finite ordinals. Well, is there anything more than that? So, well, let's have a look. So let's look at all the finite ordinals. So we have ordinal this one, and this one, and this one, and this one, and so on. Okay? So now we have an infinite sequence of ordinals. Now what's the smallest one that isn't in there? So the smallest that is not in here. Okay? what is the smallest ordinal that is not in the list of ordinals that we've already found? Well, let's look at von Neumann's definition. Any ordinal is the set of all smaller ordinals. Okay, so the smallest ordinal that isn't in here is just the set of all of these. So the answer. So the question was, what's the smallest ordinal not among these finite ordinals? Well, the answer is the set of all these ordinals. 0, 1, 2, 3. Now, usually we denote this with n, but when you work with ordinal numbers, to tell the reader you're working with ordinal numbers, we use this notation omega. Okay? So now we have these ordinal numbers. We have the finite ones. So finite ordinals. And then omega is simply the set of all finite ordinals. So what's the smallest one that comes after that? Again, the smallest one that comes after that is just the set of all. So any ordinal is the set of all smaller ordinals. So the smallest one that's not in here must be the set of all of these. So the next one that comes after this is the set of all of these. So 0, 1, 2, all the finite ones, and then omega. Of course, this is too much work to write that down, so I'll need an abbreviation, and the abbreviation is omega plus 1. Okay? So now, what do we have now? Okay, I have 0, 1, I have the finite ones, and then I have omega, and then omega plus 1. Now you can guess what comes after that. The set so what comes after that? Well, of course, we're going to denote that as omega 2. But what actually is omega 2? Well, what it really is the set of all smaller ones. So omega plus 2 is equal to the set of all smaller ones, namely 0, 1, 2, etc. And then omega, and then omega plus 1. Okay? But keep in mind, this omega plus 1 is just an abbreviation. Omega plus 1 is an abbreviation for this set. Okay? And omega itself is also an abbreviation. It's just a short notation for this set. Okay? So, but you can't really spell all of that out, because then it's going to, then the notation just gets really, really too long. So we have to have these abbreviations. Okay, so now you see how ordinal numbers are defined, and let's look at some of their properties. Okay. So we had this ordering, where alpha is less than beta, is the same thing as alpha is in beta. Okay, and whenever we have two ordinals, we either have alpha less than beta, or alpha equals beta, or beta less than alpha. So if alpha and beta are ordinals, then they're either equal or one is less than the other. So that's the property of a total ordering. Okay, so in other words, a total ordering, that's a really, really good ordering. Any two ordinals can be compared. Is that obviously true? Well, for the proof, I'll just refer to you to chapter 3. It's going to look different there because they didn't use von Neumann's definition. So I just like von Neumann's definition because it looks so dangerously close to being circular, and yet it works. I just think that's awesome. Okay, so I couldn't help but use that definition. So in any case, ordinal numbers are totally ordered. So let's see. So what's the next property? Well, ordinal numbers are even better than totally ordered. They are what's called well ordered. Well ordered, there's a number of ways to define this. One way is that if you have a set and a bunch of ordinals, then so any set whose elements are ordinals will have a minimum. And what is that minimum? It's simply the intersection of all the elements. So for example, if I have, say, the set 2 and 5 and 7, but remember this 2 was just short notation for 0, 1. And this 5 was short notation for 0, 1, 2, 3, 4. And this 7 is short notation for 0 up to 6. Okay? Now, if I pick any set of ordinals, then I can intersect all these ordinals. And notice that if you intersect these three sets, you simply get the smallest one. So if you pick, but this works not just for finite ordinals, but even for infinite ordinals. So any set of ordinals will have a minimum, and that minimum is take all the ordinals, intersect all of them, and that intersection is simply going to be the smallest element. Okay, and remember this is abbreviated as 2. So any set of ordinals. So if S is a set of ordinals, then we use this notation to means pick all the elements and intersect all of them. Then this here is the minimum element of S. Okay. Okay. So any set of ordinal numbers will have a minimum. That's one way to describe a well-ordered set. So a well-ordered set is a set is well ordered if it is totally ordered, so it's already a really good ordering, but in addition it has another really good property, namely any set of elements will have a minimum. And now lots of orderings are not well ordered. So for example, if I take the real numbers with the usual ordering, then this is a very good ordering because it's a total ordering. However, if I take, for example, all the positive reals, so I take this set and it has a really good ordering, namely the usual ordering. But now I pick a subset of that, and this guy has no minimal element. So no bottom element. Yeah. Okay. Because no matter what element you pick here, it's still going to be a positive real number, and then there's a smaller positive real number in here. So none of the elements in this set is the minimum. So this example shows that even though this is a really good ordering, it's not well ordered. Now, ordinal numbers, or the same is true for any well ordering, have another really cool property, which is actually equivalent to the well-ordered property. So let's look at let's just write down some examples of ordinal numbers. So 0, 1, 2, 3, and then I have omega plus 1. Okay, so etc. And then I have omega times 2 plus 1, etc. And I have omega times 3. And then omega times 3 plus 1, etc. And so on. And then I have omega times omega. And then omega times omega plus 1, etc. And so on. So there's a limitless supply of ordinal numbers. Now imagine you pick one of these ordinal numbers. Let's say omega times omega plus okay, I'm running out of paper. Let's say omega times omega plus 1,000,000. Okay. Okay. So I'm gonna pick this ordinal number. Now, if you pick a smaller, so now imagine imagine you have to play a game, and at every point in the game you have to give a smaller ordinal. Now, keep in mind, below this ordinal there are infinitely many ordinals below it, and yet. So the game is now give a decreasing sequence. Okay. give a decreasing sequence, but try to make that sequence really, really, really long. You would think that since there are infinitely many ordinals below this one, I could just keep going down without ever hitting 0. But actually, you can't. You see? So let's say if we're at omega plus omega times omega plus a million, you know, let's say I want to have a really long decreasing sequence, right? So I want to just keep going down, but I really don't want to end up there. And I want to make a really long sequence that keeps going down. So I can go down one step, and then one step, and then one step. But then if I do that a million times, then I'm going to hit this ordinal. Okay? So if I have to go down another step from that, then I have to pick one of these guys. Okay? Let's say I'm going to pick omega times 1,000 plus another million. Okay? Well, then after a million steps, I'm going to be forced to pick something that's less than this. Well, let's say omega times 999 plus, let's say, 1 trillion. Well, then after 1 trillion steps, I'm going to have to pick something that's less than this. So after some time, I might end up at omega times 3 plus, plus, say, a Google or whatever, some really ridiculously big number. But after finitely many steps, I have to leave this sequence and pick something that is at most in here. Well, then I might say, well, wait, if I want to have a really long decreasing sequence, then after this guy, I'm going to take omega times 2 plus 1 trillion. It doesn't matter. After finitely many steps, I have to leave this sequence and land in here or in there. So after finitely many steps, I'll end up in here. And then after finitely many steps, I'll end up in here. And no matter what number I pick in here, after finitely many steps, I can go down no further. So what you see here is that in ordinal numbers, even though there are incredibly many ordinal numbers, even though there's a limitless supply of ordinal numbers, any decreasing sequence must terminate. Must terminate after finitely many steps. So this is really really something to wrap your mind around. So you've got incredibly many ordinal numbers, and no matter which one you pick, if you keep taking steps down, even no matter how hard you try, you cannot avoid that the sequence will terminate after finitely many steps. So that property is actually equivalent to being well ordered. So any decreasing sequence of ordinal numbers must terminate after finitely many steps. So that's another so that's a key property of ordinal numbers. So now let's see. So how many ordinal numbers might there be? Well, if you pick the set of, say, all ordinal numbers, then that really quickly leads to a contradiction. I'll just refer to the book for this. But so the set of all ordinal numbers leads to a contradiction, just like the set of all sets. The set of all sets leads to a contradiction, so that was Russell's paradox. Now you think ordinal numbers are a lot more complicated than just plain old sets. Of course, ordinal numbers are sets, but okay. But this is a lot more tactical than this here. But this contradiction was actually discovered before this one. So in any case, the upshot of that is that there are so many ordinal numbers that they can actually not fit in one set. So I'm going to skip some steps here, but what this implies is that that there are more ordinal numbers than any cardinality. So so for any cardinal number d, there are more than d ordinals. So there exist more than d ordinals. So that's what I mean by there are a ridiculous number of ordinals, more than any cardinal. So yeah. So now let's let's go back to the real numbers again. So we could pick some real numbers, say b0. And we could, obviously we haven't run out of elements yet, so we can pick another one, b1, another one, b2, and so on. Then we can pick an element b omega plus 1, etc. So far we've still only picked countably many, and then we can do the same for 2 times omega, 3 times omega, and so on. And then we get elements, say b omega times omega, b omega times omega plus 1, and so on. And so for any of these ordinals, you can pick a real number. And what I've just described all combined, that's still countable, and R is uncountable. So there's still way more here. So so any ordinal, you know, that is easy to write down is countable. But for any cardinal d, there are more than d ordinals. So there must also be uncountable ordinals. So for example, the cardinality of this here is C, but not only do there exist C ordinals, there exist even more than C ordinals. So so that means that if I just look at all these countable ordinals, like all of these examples that I've given so far, all of these guys are countable. I really have only given you countably many examples. So with those ordinals, we're never going to run out of reals. But there are way more than d ordinals. So if I could somehow keep going, then at some point I actually do run out of ordinals. So there is actually a bijection between R and some a set of ordinals. Now, mind you, not all ordinals. Okay, not all, because if I have this bijection, then this guy has C elements because this guy has C elements. And for any cardinal there are more than that many ordinals. So this is definitely not all ordinals. But this set of ordinals is well ordered. And then this bijection, you can use this bijection to give a new ordering on this. So instead of the usual ordering, we're going to order them according to their labels. So this one comes first, this one second, this one third, and so on. So these labels give you a new way to order the reals, and that ordering is well ordered. So there exists a well ordering on the reals. So I'm of course skipping some stats here, but the chapter 3 will give you more. We'll give you more details on that. Okay. So let me see. I think I think that's pretty much what I wanted to say. So in any case, so this is I think this is really a cool stuff. You know how you can have a definition like von Neumann's definition, and you're really so close to the danger zone, but because circular definitions pretty much always cause contradictions, and so this is really close to the danger zone, and yet it just works just fine. So I guess I'll stop here. I think this video is long enough. So